Good day. I am Peter Ayan Iragandang and I am going to present a solution of problem 11.25. So this is the problem presented in problem 11.25. So we are given with temperature of our system, which is 150 degrees Celsius, our pressure, which is equal to 30 bar, and the composition of ethylene in our system, which is 0.35. So we can now solve for the composition of propylene in the system, which is equal to 1 minus 0.35, which is equal to 0.65. So we are required to find the fugacity of species 1 and 2 in the solution, and the fugacity coefficient of species 1 and 2 in the solution. So applying equations 11.63 in order to find the required items, we will use this formula which is given from our textbook. In here, we can solve for the fugacity coefficient of each species in the solution. But first, we need to find these parameters. And we can solve this parameter by using this equation which is found in page 406. And also, before we can use this equation, we need to find these values here. And we can do that by using equations 11.69 a and b. So this is what we have here. And before we can use equations 11.69, we need to find these parameters which are second virial coefficients. So which is needed to solve for this equation. What we can do first is to list down the values of the characteristic properties of both species in the solution, which are ethylene and propylene. This can be obtained from table B1 of our appendix in our textbook. So this is the values for ethylene and these are the values for propylene. So we can use those values in order to solve for the characteristic properties of each ij pair by using equations 11.70 up to equations 11.74. We can solve for the eccentric factor, the critical temperatures, the critical compressibility factor, the critical molar volume, and the critical pressure of each ij pair. So by the application of equations 11.70, we can solve for the eccentric factor of each ij pair by using this equation. And here we can see the calculation of the eccentric factor for I is equal to 1 and j equals to 1, which results to this value, 0.087. In the same manner, the other three ij pair was calculated, which gives the values here. Next, we solve for the critical temperatures of each ij pair, but first we need to note that this formula, equation 11.71, is supposedly multiplied by 1 minus Kij, where Kij is the empirical interaction parameter of each species, but we will assume that ethylene and propylene is chemically similar, which will give a value of Kij equals to 0, which then simplifies the formula into this form. So here, it is shown the calculation of the critical temperature for I is equal to 1 and j equals to 1, which resulted to 282.3 Kelvin. And in the same manner, the other three ij pairs is calculated. Equation 11.72 will calculate the critical pressure of each ij pair. But since it is a function of the critical compressibility factor and the critical molar volume, so we need to solve first for the latter. So here, we use equation 11.73 to solve the critical compressibility factor of each ij pair by using this equation. So we can see here the calculation of the critical compressibility factor for I is equal to 1 and j is equal to 1, which results to 0.281. In the same manner, the other three ij pair is calculated. Equation 11.74 allows us to calculate the value of the critical molar volume of each ij pair, which is given by this equation. So here, is shown the calculation of the critical molar volume when I is equal to 1 and J is equal to 1. And it resulted to this value, which is equal to 131 centimeter cube per mole. And in the same manner, the other three were calculated. And since we already calculated the required parameters in order to calculate the critical pressure of each ij pair, we can then solve for the critical pressure for each ij pair. So here it is shown the calculation when I is equal to 1 and J is equal to 1, and it resulted to 50.345 bar. In the same manner, the other three critical pressures for each ij pair is calculated. Here are the values. Here we can see a table of the calculated values for each characteristic properties for each ij pair. And since we already obtained the critical temperature for each ij pair, we can then calculate the reduced temperature for each ij pair by using this equation. So calculating for the reduced temperature, which is the quotient of the temperature of the system over the critical temperature of each ij pair. So we can calculate it, and these are the values for each ij pair. The second virial coefficients are a function of the reduced temperature, and since we already calculated the reduced temperature of each ij pair, we can calculate the second virial coefficients for each ij pair, and this is VO is given by this equation here, and so we can solve for the second virial coefficient for each ij pair. So these are the values for each ij pair. Same as we did for BO, we can solve for B1 by using this equation, and it resulted to the following values for each ij pair, since we already know the reduced temperature. So here we tabulate the reduced temperatures that we solve for each ij pair, the second virial coefficients that we also solve for each ij pair. And so since we already know these values, we can use the equations 11.69. So we can solve for the value for B. So here is shown the calculation for B when I is equal to 1 and J equals to 1. And it resulted to negative 59.77 centimeter cube per mole. And in the same manner, the other three values for B for the other three ij pair combination was solved, and it resulted to the following values. As stated before, we need to solve the value of this parameter in order for us to use the equation 11.63 to solve for the fugacity coefficient of each pieces in the solution. And since we already know the values of these three here, which were solved previously, substituting into the formula will give us the value of this parameter, which is equal to 20.96 centimeter cube per mole. Since we are already given with these values here, and this is a gas constant, and we already solved for the values of these parameters here, and we already know that this is given, we can calculate for the fugacity coefficient of species 1 in the solution, and by using shift solve in our calculator, we can obtain that the value for the fugacity coefficient of species 1 in the solution is 0.9576. In the same manner, we can solve for the fugacity coefficient of species 2 by substituting the appropriate values, which we already solved and which are also given. So substituting and by shift solve in our calculator, we solved that the fugacity coefficient of species 2 in the solution is equal to 0.8747. Knowing that the fugacity coefficient of the species in the solution is related to the fugacity of the species in the solution by equation 11.52, we can solve for the fugacity of the species in the solution. So here, we can solve for the fugacity of ethylene and propylene, and these are the following values that we obtain. So for B, we are required to find the fugacity and the fugacity coefficient of each species in the solution with the assumption that the solution is ideal. And for ideal solutions, it is from equation 11.84 that the fugacity coefficient of species I in an ideal solution is equal to the fugacity coefficient of pure species I in the same physical state as the solution and at the same temperature and pressure. So we have this equation for the calculation of the fugacity coefficient of species I in its pure species state. The only difference from the previous method that we used in the application of equation 11.63, here we use the reduced pressure of the pure species. So in order to use these equations here, we need to calculate the reduced pressure for the pure species, since we already know the values of the reduced temperature and the second virial coefficients, which were solved previously, and also the eccentric factor for the pure species. So this is the equation that we can use to solve for the reduced pressure for the pure species, in which I and J will be equal to each other. So these two values here that we calculated are the reduced pressure that we need in order to use these equations. And since we already know the values of the reduced pressure, we can now then solve for the fugacity coefficient of species 1 and species 2 in the solution, in which it is assumed to be ideal. So substituting the values that we calculated previously, we can obtain that the values of the fugacity coefficient of ethylene and propylene in the solution is 0.9503 and 0.8728 respectively. And finally, with the knowledge of the relationship between the fugacity coefficient and the fugacity of the species in the solution, which is given by equation 11.52, we can now solve for the fugacity of each species in the solution. So the fugacity of ethylene in the solution is equal to 9.97 bar, and the fugacity of propylene in the solution is equal to 17.0196 bar. So thank you and good day.
Hey guys, I am going to discuss the solution to problem 11.33. For an equimolar vapor mixture of propane and N-pentane at 75 degrees Celsius and 2 bar, estimate Z, HR, and SR. Second virial coefficients in centimeter cube per mole is given below. In this problem, we have an equimolar system of propane and N-pentane at 75 degrees Celsius and 2 bar. We are asked to estimate Z, the residual enthalpy and entropy. The pressure of the system is relatively low at 2 bar. Therefore, we assume the validity of the virial equation up to the second term. Here are the list of equations that will be used for the problem. You can pause this part to go through the equations. First, we calculate for B using equation 11.62. We substitute the known values of temperature and pressure to get negative 504.25 cubic centimeter per mole. Since B is known, we can go ahead and solve for Z, which is equal to 0.965. Notice here that equations 6.55 and 6.56 require a value of dB over dt. Since we have an equation for B, we integrate this equation with respect to temperature and solve for dB over dt. Integrating individually, we get the following values. The values for B sub 11, B sub 12, and B sub 22 are found from the given table. Notice that the temperature range is from 50 degrees to 100 degrees Celsius. Now, we can solve for dB over dt. Plugging the values calculated earlier, we get 3.55 cubic centimeter per mole K. Then, we can solve for the residual enthalpy. HR is equal to negative 347.93 joules per mole. Finally, we also calculate the residual entropy. Plugging in the known values, we get SR equal to negative 0.71 joules per mole Kelvin. Hey guys, now I am going to discuss the solution to problem 10.39. Calculate phi and fugacity by the Suave-Redlich-Kwong equation of state for the substance and conditions given of the parts of problem 11.38, and compare results with values taken from a suitable generalized correlation. In this problem, we are going to solve acetylene at 325 Kelvin and 15 bar. In this problem, we want to calculate for the phi and fugacity of acetylene at 325 Kelvin and 15 bar using Suave-Redlich-Kwong equation of state. We assume that since the system has moderate pressure at 15 bar, the Pitzer correlation for the second virial coefficient is valid. We are required to compare the results from SRK to values obtained from an appropriate generalized equation. Here is the list of equations that will be used for this problem. The first box is for the SRK equation of state, while the other is for the calculation using generalized equation for gases, particularly the Pitzer correlations for the second virial coefficient. You can pause this part to go through the equations. I also went ahead and listed all the pertinent data that are needed for the solution. You can also pause this part to see all of the values. First, we need to calculate for the reduced temperature and pressure. Since we already have the value of the critical temperature and pressure, as well as the temperature and pressure of the system, we can calculate for the reduced temperature and pressure. Tr is equal to 1.054, while Pr is equal to 0.244. Also, we need to solve for the alpha to be used in the SRK equation of state. Plugging all the known values, we get an alpha of 0.959. Next, we calculate for Q and beta. The equations are given by equation 3.54 and equation 3.53. Substituting the values, we get a Q equal to 4.489 and beta equal to 0.0201. Since we now have all of the needed values, we can calculate for Z. Plugging in the values for eta and sigma, we can reduce the equation to this. Z can be calculated by iteration. Using Microsoft Excel for the iteration, we get a value of Z equal to 0.927. Now, we can calculate for I. First, we reduce the equation by plugging in the values of eta and sigma. Substituting known values, we get an I equal to 0.0215. Lastly, we calculate for phi and fugacity. Using equation 11.37, we calculate phi equal to 0.93. Next, using equation 11.34, the fugacity is equal to 13.95 bars. To compare values, we use an appropriate generalized equation for gases. In this case, we are going to use the Pitzer correlations for the second virial coefficients. We need a value of B0 and B1. Using equations 3.65 and 3.66, we get B0 equal to negative 0.3049 and B1 equal to 1.0893 times 10 to the negative 3. Lastly, we solve for phi and fugacity. Using equation 11.68, we get a value of phi equal to 0.93. Fugacity is then equal to 13.95 bar. Notice that we calculated equal values of phi and fugacity using SRK equation of state and the generalized equation. This means that using the generalized equation can also give us a close approximation of the values. Also, recall that the Pitzer correlation for second virial coefficient is applicable to systems with low to moderate pressures.
Problem 11.44, presented by Lawrence Peter B. Ares. 50 mole percent of enriched air containing equimolar N2 and O2 gas are produced by continuously combining air containing 79 mole percent of N2 and 21% O2 with a stream of pure oxygen. All streams are at constant conditions, 25 degrees C, and a pressure of 1.2 atm. There are no moving parts. A. Determine the rates of air and oxygen in moles per second. B. What is the rate of heat transfer for the process? C. What is the rate of entropy generation Sg with the units watts per Kelvin? State all assumptions. Suggestion. Treat the overall process as a combination of the mixing and mixing steps. In this problem, we are given two inlet streams of air with a mole fraction of 0.79 N2 and 0.21 O2 and a known flow rate denoted as N1, and a pure oxygen stream with a known flow rate N2. These two streams are mixed at constant conditions of 25 degrees C and 1.2 atm. So after mixing, the effluent from the mixer produces an outlet stream with a flow rate N3 of 50 mole per second with an equimolar composition of O2 and N2. We are asked to find the flow rates of air and the oxygen stream, the rate of heat transfer for the process, and the entropy generation. I assume ideal gas behavior throughout the process. A. Determine the rates of air N1 and oxygen N2 in moles per second. The first step is to conduct an overall nitrogen balance. Doing a nitrogen balance means that the input nitrogen is equal to the output nitrogen. Using the given values from the problem gives us this equation. Solving this equation in terms of N1 results into this flow rate. Thus, the air flow rate N1 is equal to 31.6456 mole per second. For the oxygen flow rate N2, an overall mole balance should be done. This means the mole input is equal to the mole output. This notation results into this equation. So rearranging these terms in term of N2, since N2 is still unknown, results into this equation. As N3 was already given and N2 was solved from preceding slides, the N2 can now be calculated. Substituting the values, it results into this. Therefore, the flow rate of pure oxygen field is equal to 18.35443 mole per second. So in summary, the air flow rate N1 is equal to 31.6456 mole per second, and the oxygen flow rate N2 is equal to 18.3544 mole per second. Letter B. What is the rate of heat transfer for the process? Since the gases are assumed to be ideal, the enthalpy of mixing is non-existent. This is due to the fact that ideal gas assumes no molecular interactions. Thus, this implies that no heat is absorbed or produced during the mixing process. Therefore, delta H, or the heat transfer, is equal to 0. For letter C, what is the rate of entropy generation, Sg, with the units of W per Kelvin? The general formula for entropy is the entropy of an ideal gas is equal to the summation of mole fraction multiplied by the entropy changes of an ideal gas subtracted to the ideal gas constant multiplied by the summation of the mole fraction of the gas multiplied by its natural logarithm. This is given by equation 11.26 on the textbook. However, since temperature and pressure remain constant throughout the process, this term can be cancelled out, as no entropy is generated due to changes in the system temperature, pressure, and other conditions. Therefore, the only term left is this, which takes into account the entropy changes due to mixing, or simply, this term is the entropy of mixing. In this problem, consider two processes, the mixing and mixing process. Let us first take into account the mixing process of air to O2 and N2 in the inlet stream, where O2 is Y1 and N2 as Y2. This formula was given from the previous slide. However, this is used for mixing process, while in this case, it is a demixing process. Therefore, the sign of this equation should be inversed, as the mixing separates the compounds, thereby reducing the molecular randomness and disorder. Thus, the entropy is decreased in the system. Therefore, for the mixing process, the entropy of the mixing formula should be the same but with positive sign. In this case, the formula expands to this one. Substituting the y1 and the y2 values obtained from the given values results into this equation, where R is equal to 8.3145 joules per mole K. Simplifying, the entropy of the mixing of air is equal to negative 4.2739 joules per mole K. Now, let us consider the mixing process of air that occurs in the mixer, which resulted into the outlet stream. As same as before, we denote O2 as Y1 and N2 as Y2. The entropy of mixing is given by the formula. Expanding, it results into this equation. Substituting the given values and the constant R results into an entropy of mixing equal to 5.76317 joules per mole K. In summary, the entropy of mixing and the mixing process are as follows. The entropies can be added to determine the entropy generation. However, these problems specifically require the units of watts per Kelvin. Therefore, before adding the entropies, the molar flow rate from individual processes should be multiplied to its respective entropy generation before summing it up. This leads us to the equation that the total entropy change, or the entropy generated, is equal to N1, or the molar flow rate, multiplied by the entropy of the mixing plus the flow rate N3, which is the effluent flow rate, multiplied by the entropy of mixing. These values were obtained from the previous calculations and given values. Substituting, it gives us the total entropy generation of 152.9277 watts per Kelvin. Therefore, the entropy generation for the mixing process of pure oxygen and pure air is equal to 152.9277 watts per Kelvin.